Alright, hey everyone. We're here for 8.2 graph simple rational functions. We're starting here with the graph of y equals 1 over x. It's the parent function. And the first thing we need to address are the asymptotes. So these are basically x or y values that can't exist for one reason or another. And we'll start with when x is 0. And a quick check of what happens if you put 0 in the problem for x. Reveals you get 1 divided by 0, which is undefined, doesn't exist, so x cannot equal 0, that's an asymptote. And then the other one we'll test is y equals 0. And when you put the 0 in for the y value, first everything looks alright, and then if we test that out and multiply by x on each side, you end up with x times 0, anything times 0 is 0, while on the other side, the x in the bottom, the x over here, they cancel each other, you just have 1. And of course 0 doesn't equal 1, so we've found our other asymptote, that's y equals 0. So I'm going to go ahead and draw them on here. There's the y equals 0, it's basically the x-axis where y is always 0. And then there's the x equals 0. It's the y-axis where x is always 0. So now from here, we're going to find some other values using an xy table. And I'm going to build my x values around the asymptote x equals 0, just without using that exact value. So I might choose other values like -2, -1. I'll skip right past 0, and instead I'll do 1 and 2. We can find our y values then using input-output. In the first one, when -2 substitutes for the x value, well, no other work needed. You end up with something that says y equals -1/2. So I go ahead and write that in there. You can check the other ones, and you should find other values like when x is -1, so is y -1. When x is 1, y is 1. And finally, when x is 2, then y is 1/2. So I go ahead and graph these. I'll go left 2 spaces, down 1/2. About there. Then left 1, down 1. That's right there. Then I'm looking to go right 1, up 1. And finally, right 2, up 1/2. So then what I start to see as I think of how to connect these points is these points need to be connected, but I have to stay within the boundaries set by the asymptotes. So I get a curve that looks like that on that side, and over here in quadrant 1, we get a very similar curve, again bounded by those asymptotes, but connecting the points that we can. This graph is called a hyperbola, and as evidenced by the graph that we see there, that except for where the asymptote exists, everything else is possible. We've got a domain of all real numbers except for 0. We've also got a range of all real numbers except for 0. And so we'll take a quick look over here at Desmos. And there's that parent function, y equals 1 over x. And there's a much cleaner looking version of that graph, much better than the one that I just drew. So we want to take a quick look here using the speed and efficiency of Desmos at a couple other rational functions like y equals 4 over x. Some quick thinking about input like x is 1 can give us an idea of what's going to happen. In the parent function, when x is 1, we've already seen 1 divided by 1 is 1, and there's our point at x is 1, y is 1. There it is right there. In the second function, if x is 1, then it becomes 4 divided by 1. We get y is 4. And so if I go over 1, but now I have to go up 4, you're going to see it's way up here, farther from the origin, farther from the axes. And sure enough, if you continue to graph the rest of that, that's exactly what happens. You'll notice the asymptotes are the same. X equals 0 is an asymptote, y equals 0 is an asymptote, which means the domain and range are the same. Both of them are all real numbers except for 0. But you see that blue graph, all those blue points, they're farther from the origin, farther from the axes than the parent function was. So we'll take one more look here, this time at y equals 0.5 divided by x, and we see kind of the opposite effect. Let's again check what happens when x is 1. And this time when x is 1, well, anything divided by 1 stays the same, so I get 0.5. So that's when x is 1, I go over 1, but I only go up 1/2. You see I'm right down here. Now I'm closer to the origin, closer to the axes. And sure enough, the entire graph is just like that. Again, you'll notice the same asymptotes, the same domain and range, but everything's been pulled closer to the origin, closer to the axes. So now we're just going to go back here to ActiveInspire for one last example. And that's what happens, you see here, when there's either a horizontal shift or a vertical shift, or in this case, one of each. And that has an effect on our asymptotes. So for starters, if the asymptote caused by the denominator was that you can't divide by 0, well, now we're looking at what x value would make that become a 0. So since there's a +2, we think the opposite of that, and we say x equals -2 is an asymptote. That would be -2 plus 2 is 0, and again, you're dividing by 0. If the other asymptote was y equals 0, well, now that -1 is going to shift the entire graph down one space, so that asymptote's now at y equals -1. So I'm again going to start by drawing those asymptotes, and there's x equals -2, there's y equals -1. And now I'm back to building my xy chart. And I'm going to choose x values again around -2, but then skip right over -2. And I'm going to show some input-output to show that when x is -4, well, let's see what happens there. In the denominator there, we have -4 plus 2, that is -2. Then we have negative divided by negative is positive, and 4 divided by 2 is 2. Finally, 2 minus 1 is 1. So there's when x is -4, y is 1. You can do this again for the others to find that when x is -3, y is +3. When x is -1, y is -5. And when x is 0, y is -3. So now we'll see what happens when we put those on the graph. I'm going from the origin, and that's left 4 spaces. So that's left 1, 2, 3, 4, and then up 1. So that's right about there. And then we're looking to go left 3 and then up 3. So left 3, 1, 2, 3, up 3, right about there. And now left 1, down 5. That's left 1, down 1, 2, 3, 4, 5. And finally 0, -3. So don't go left or right, just go straight down 1, 2, 3 spaces. And now using those asymptotes as our boundaries, we're going to connect the points that we can while staying within those borders. And we'll do another one on this side. Okay, and so this time we're setting our domain and range bounded by these new asymptotes. So we're looking at all real numbers except -2 for the domain, and then all real numbers except -1 for the range. So that gives us a little bit of information there about graphing rational functions. At this point, if you could try the problems in the assignment, I'd appreciate it. Take a picture, upload it to Google Classroom when you're done, and thank you very much for watching.